You'll need to draw your own force diagram for question 6. I'm going to draw over the top of their diagram just because of lack of space, but it's really better if you draw your own. In an exam, if you draw over the top and then change your mind, it's quite hard to reverse it. So I would draw your own diagram. It's part of your working as well. Okay, so your force is acting on Q here. You've got its weight, which is 0.2 G, and then there's tension pulling it up. Initially, P is held, so whatever forces are mentioned here are presumably involved, and there's some extra forces just holding it all in place. It's in equilibrium. Okay, so this is before it's released. This is kind of what's going on. It's in equilibrium initially. So initially, if you think about the forces acting on Q, it's in equilibrium. We've got T is equal to 0.2 G, and that gives you 1.96 newtons. Now, what then happens is that P is released, so it won't be in equilibrium anymore. P isn't being held by someone. Just the forces mentioned are involved. So there'll be normal reaction. This is part 2 now. This is the second bit. This is part 1, but after it's released. There's the tension in the string is pulling it up the slope. Friction is pulling it back. Now friction here is mu r because the thing is going to be moving, 0.4 r, and the weight acts downwards, which is 0.2 G. That's 30 degrees, and they're both going to be accelerating, equal acceleration. The string is not going to stretch, it's inextensible, so they move as one with the same acceleration. That's your force diagram for the next part of the question. So the initial bit was when it was equilibrium, now it's accelerating. We've got to find A, so we're going to get some equations. What you can say is if you resolve perpendicular to the slope for particle P, what's going on there is the forces will balance out because it's accelerating at right angles to that direction. It's accelerating up the slope, so at right angles the forces are going to balance out. So R is pushing out of the slope, 0.2 G cos 30 is acting into the slope. So we have R straight away. We're going to resolve parallel to the slope for P using F equals ma. So take care it's not going to be in equilibrium here. Forces up the slope are more than the forces down because it's accelerating up the slope. So we've got T is pushing up, and then the ones pushing down are the friction and a component of the weight. And that's equal to ma. Right, what we could do now is eliminate this R using our equation up there. That can go in. So we've got T minus 0.4 times 0.2 G cos 30. Now the theta there, it was 30 actually, so I'll replace that. We've got now 0.2 times sine 30. Sine 30 is a half times 0.2 is 0.1. It's 0.2a. So we have one equation there with two unknowns, t and a. We get another equation like that. We're going to resolve vertically for q using F equals ma. And we're going to have there now the forces down are more than the forces up. Okay, it's going to accelerate downwards. So 0.2 G take T is 0.2A. So now we have a pair of equations, 1, 2, with two unknowns, A and T. We're trying to work out T, the tension, so it makes sense to eliminate A. We could substitute one of these in here. So if you do that, you'll get 0.2 G take T is equal to T minus... Substitute that. If you were to use your calculator there, we could just do that. I think what we'll get, I believe it's root 3 over 25 G. That's this lot. Minus 0.1 G, and they're equal. Now I tend to keep things exact. If you want to kind of use decimals, you can. I'll get an exact expression at the end. I tend to keep G until the very end as well. So to finish it all off, you just need to add T onto both sides now and get 2T. And you get 2T equals. You can revert to decimals there. If you finish it all off, you'll get 1.81 newtons to 3SF, but you should be able to solve the equations there at the very end.